on space-based compute infrastructure, edge AI, and orbital data centers. As demand grows for low-latency analytics, sovereign data control, and AI-driven decision-making, computing is gradually exceeding beyond terrestrial networks. This session explores the rise of in-orbit processing, edge AI, orbital data center, architectures, and the opportunities they present for India in the next generation of space infrastructure. To chair and moderate this session, it's my pleasure to invite Dr. Dipyaman Banerjee, IIT Kharagpur. I please invite you to the stage. We also welcome our distinguished speakers and panelists, Mr. Sharat Reddy, co-founder and lead product development, Take Me to Space. Lieutenant Commander Shashank Kulshrestha, retired VP Government Operations, Skyserve. Mr. Antonio Stark, Global Space Strategy Expert. Thank you all of us for being here. It's an absolute honor to have you with us today. Now I kindly pass over the stage to our esteemed panelists and chair. Thank you.
Hello. Okay. A very good afternoon, ladies and gentlemen. I know it's a long day. It has been a long day. Many of you have woken up very early in the morning. But we saved the best for the last. Okay. So this is a very, very interesting topic, and we have an esteemed panel with us to discuss on it. This is called space-based computing infrastructure, edge AI, and orbital data centers. So this is a stuff of fantasy, science fiction, maybe just a few years ago, right? And now we have probably two camps emerging. Where in February, Sam Altman's saying that this is ridiculous and it's a fantasy, whereas Elon Musk and Sundar Pichai taking the other side. Elon Musk, in fact, launched their AI-1 satellite design, where they just unveiled it. And it is huge. It has like 70-meter wingspan and solar panels in it. And the compute, the peak processing power in that satellite rivals high computing performance of terrestrial server racks, like GV300 from NVIDIA. And on the other hand, we also have Sundar Pichai, who's an alumnus of the institute where I work, IIT Kharagpur. So he has also come up with this Suncatcher project, where he's saying that he will do compute on the space using solar energy. So there are multiple apprehensions, there are multiple, I would say, thoughts, position taken. So we will discuss all of that. I would first start with a round of introduction with our esteemed panel. Sharat, if you can start off and tell us everybody what you are working on.
Hi everyone. I'm Sharat from Take Me to Space, and our vision is to build orbital data centers. Now, whether that takes the shape of what Musk had presented last week, or whether it will be something different, I believe the entire industry is still in the discovery phase of what those satellites would look like. We believe it's an eventuality where uh, data centers are going to be in space, hook or crook. Now, whether that will be 50 kilowatt nodes or a 1000 kilowatt node or how many gigawatts are going to go, I believe that's a discovery process that's ongoing. We at Take Me to Space believe that because this is an infrastructure play, that anyone who's doing this must absolutely own the entire piece, be fully vertically integrated in terms of their hardware, software, everything, and they build everything themselves. That's when you're able to give to your customer a price that is competitive with the price that they get on ground or terrestrial data centers. So we're on the mission to build this out in phases at Take Me to Space. We're launching one satellite with, let's say, a 40-watt compute this year. We're ramping it up over the next few years where we do 40-watt, 1.5 kilowatt, 5 kilowatt, and then 50 kilowatts. So the idea is to learn at each node and to be able to do multi kilowatt satellites over time. So that's what we do at Take Me to Space, and I lead the product development at Take Me to Space.
Excellent, Sharat. I'll next ask Lieutenant Commander Shashank Kulshrestha, who is currently working as VP of Skyserve Government Operations. So if you can just give an introduction.
Thank you, Dr. Dipyaman. Thank you for that introduction. So Skyserve is an edge computing company. We've done 5 missions so far, and we plan to undertake edge computing not only for the Earth observation, but extend the applications to maritime domain awareness, even to space observations. We've already done this, and I very firmly believe that it is doable, and the applications can be enormous. The use cases can be infinite.
Thank you, Shashank. Next we have Antonio. So Antonio, if you can just give a brief introduction of yours.
I'm Antonio Stark. I'm a Korean-born, US-educated, Japan-residing global space strategy expert. I work on a lot of different companies, ranging from lunar missions to Earth observation satellites to defense to national security applications for space assets. I'm here on more kind of like the outlier of the group, so we have a couple of people who think orbital and edge computing for space is like the future of space exploration, and then I have also been following the space for a very close time. I also had multiple problems that I've encountered during my tenure in going through multiple satellite companies and lunar companies, and I know that there's also technological, and economic challenges in trying to make that challenges to that dream becoming a reality. So I'm here to really discuss that future, what is possible, what is not possible, and what can we do to actually make this into a success if a market for that does exist.
Thank you, Antonio. Antonio also worked in T-Hub Hyderabad, and he says he's very happy to be back in India.
I am very happy to be back in India. I used to live in Hyderabad, and I go around India quite a lot. I think I actually know about half the room here, so no need for too much introduction, yeah.
All right. So with this unprecedented data generation that is happening through AI systems, satellites, sensors, and communication networks, of course. So we are now asking the question: can computing itself move into the space? Which is amazing, I think, as a concept. And my first questions on that goes to Lieutenant Commander Shashank. So what problems are orbital data centers and space-based computing infrastructure are actually trying to solve?
So it's not one singular problem, if I can put it that way. It's a lot of problems in a very tiered structure. Let me begin with the problem of the scale. You know, every day we are walking towards constellation of thousands of satellites who would need ground stations, and they cannot rely on ground stations for every other activity. In simple words, what I'm trying to say is we have created more satellites than we have ground stations. Then obviously there is a problem of bandwidth and the cost. So satellites today are aggregating data at some phenomenal rate, some petabytes and zettabytes. And the ground stations are not equipped enough to handle that kind of data. And downloading that kind of data is cost-intensive process. Then there is the underlying problem of the heat, which we all know about and we've been discussing all around. The ground stations use resources which are finite, power grids, cooling. this is creating a constraint on the environment as well. So these are some of the challenges which have forced the humans to think of data centers beyond the Earth. One of the best use cases that we have today is edge computing. It's already solving for latency. We've already, uh, proved it that computing can happen in space. So that is the future.
Thank you. My next question goes to Antonio. Antonio, how different it is to design, say, a data center in space versus if I want to do it on Earth? And specifically, why would I think of creating a data center in space in the first place? Where does that thought comes from?
So Lieutenant Commander Shashank has actually mentioned a very big reason is that we are generating an immense amount of data in space. The thing is that very little of it is actually used, and this is very predominant in the Earth observation sector. I think I've seen a study that quote, even at a very generous level, we utilize about 2% of all the data that we generate from Earth observation. Most of it goes unused, and that is only for the data that we already have downlinked to Earth, which is why Earth Edge AI and computing is now being used to kind of figure out how can we filter these data so that we can only, one, collect only useful data, like when we know that something interesting can happen, can we collect data only at that point, and also when we actually process through them, can we only downlink the data that we can use and in a timely manner, because if we try to go through, sift through all the data and then give it to the commanders, I mean, in the military, we all know that timing really is the key for a lot of different applications. Edge computing really drastically minimizes the time delay in that process. At the same time, a lot of this could be done on terrestrial data centers as well. So the benefits of space data center does have to go through multiple challenges, and I do frame it into the technological challenge and the economic challenge. The economic challenge is that you need to have a market for it, and I will tackle this in a future question. Technologically, there's a few. One is that the hardware is very different. Space is a very radiation high environment, and a lot of the GPUs and the other AI components that we use for Earth simply is not radiation hardened enough. It cannot survive the vibrations. The buses that we currently have for the satellites simply don't operate. When you first build a data center on Earth, you can use it for like 10 years. If you launch it on a satellite, your lifespan is going to be much smaller than that. You also have to give up radiation. You also have a massive power storage. There's also the technological shortage of the algorithm, which is where Skyserve also tries to go in. There's a lot of disruptions that you can have with solar flares and other things, or even just small particles that can just disrupt like one line of code while it is executing, or one bit in a data, and that will again corrupt the whole data set. So there's a lot of these technological challenges that is presiding over the orbital data set. So there is a huge potential, and if this becomes successful, it can solve so many problems. At the same time, the problems that you need to solve in order to get that into maturity is also extremely high.
Got it. Right, you are saying that the road is tough, but if we get there, there is goodies at the end. So okay, all right. So I will, Sharat, you are next. So Sharat, I hear that you have taken to space, and SIA-INDIA have recently worked on a particular policy level report on orbital data center, and you are going to publish it. I'm sorry to break the news, but in this conference itself. So my question to you would be that Anthony already touched upon some of the engineering challenges. You can expand on that. That what are the engineering challenges that are there to create orbital data centers, but if you can also touch upon the economic and the policy level challenges that are there, and how we can mitigate them.
Right. So from an engineering standpoint, Antonio brought up very valid concerns with respect to radiation. I'll add two more to them, which is power and thermal. Power, thermal, radiation are sort of the three key areas of engineering that really need a lot of innovation. And more than innovation also, it's about the mindset of product design for space needs to come in. What I mean by that, right? Data centers in space cannot be built like we build satellites today for GEO and the other LEO satellites. Data centers in space need to come off a manufacturing line. It's a grounds up rethink of how you design and build satellites. Now, in terms of power, a part of it could be solved with dawn-dusk orbits, but again, you'll always run into sort of capacity limits where, let's say SpaceX is now asking for a 1 million satellite constellation authorization, right? So dawn-dusk orbits ensure that you do not have to carry the sort of batteries so that you have 95 to 98% solar, light coming in so that you have power all the time. From a thermal standpoint, this has been debated quite a bit, but the fundamental physics sounds plausible. What happens is when you go into the size, when you look at the size that now SpaceX has proposed, which is some 70 meters odd, that is when you suddenly think, will we be able to build this and actually deploy this? There, I would like to tie it to another product design challenge where if you look at it, the designs out there, if you look at StarCloud, if you look at SpaceX, if you look at us, which we will shortly unveil in the next 2 days, there is no right answer to whether it should be one massive central satellite bus with massive panels for power generation and for radiators, or can it be a very extremely distributed compute where you have, let's say, 1,000 GPUs laid out flat? Like, there are so many competing thought processes from an engineering standpoint to tackle this thermal problem. The route that SpaceX is taking is, they're saying pumps, heat pumps. Now, the sort of challenges in a production line for heat pumps is massive, according to me. You have one leak and that's it. Your heat loops have gone for a toss. Whereas if you are relying on passive thermal dissipation, you ensure that even if one GPU goes down, the others work. And this also sort of ties in with the radiation problem statement as well. Definitely radiation shielding is required for these GPUs, given the sort of transistor densities that we are hitting with these nowadays, the feature sizes that we are looking at, the gate sizes of these transistors, the damages that these high energy particles or even low energy particles can do is immense. Now, how do you shield these at a low cost weight and still get the thermal performance out of these GPU dies is paramount. Now again, like a lot of work is being done on this, but I would also like to say that the radiation problem statement is sort of blown out of proportion. Again, personal opinion, because if you see NASA's Ingenuity helicopter on Mars runs on a Qualcomm Snapdragon chipset, which is on a lot of your phones here, and it did some 76 or 80 odd flights. Very valid point that Antonio brought up here is how long do these satellites have to survive? Is it 10 years, 15 years? Is it 5 years, 3 years? And from that brings me to the final thing of how do you design these satellite buses? Do you design buses for today's H100s or your Grace Blackwells? Or do you keep your systems architecture agnostic so that 3 years later, your GPUs are going to evolve every year? Like you lose your competitive edge the moment you send up the satellite, that's it, your time starts ticking, right? Your GPUs are evolving every year. Now, whether your satellite bus and your manufacturing line and your thermal and your architecture design can account for the new generation of GPUs that comes 2 years later, so that you can keep replenishing your satellites at a cost that is manageable. I think these are sort of the engineering challenges I see. From a policy standpoint, from an adoption standpoint, especially from policy, I believe at a nation level, doing pilot deployments and sort of trying to understand customer use cases. We are of the opinion that the Earth observation industry is the one that is ripe. I'm sure even Shashank would agree that there's a lot that could be done with existing satellites data, Earth observation satellite data, which even newer satellites are gathering, by adding a layer of intelligence to them. But to be able to deploy access to orbital data centers, even in a smaller scale, in governments or in agencies that work parallel to the governments, that will enable us to actually understand the user need and how do they and what use cases it drives. For example, the moment the ingress-outgress data problem is solved, let's say we're, like you said, 2% of data is actually used, 30% of data is actually clouds, images of clouds that you don't know anything with. The moment we are able to say, this is useful data that we capture, it is going to open up new use cases and new applications that were not possible till today, is our hypothesis. Now, we have to be close to the users and customers on the ground with sandbox deployments so that they can actually explore and find out what those applications could be. Like a few people sitting in one room cannot dream up these applications. It has to be open access for all, and with, of course, with certain guardrails so that you can actually discover what the new applications for satellites are.
Thank you, Sharat. I think it's excellent and very detailed, insightful analysis. Specifically, thank you for bringing up the user perspective in here. So these are new technology frontier. We understand, and like any new technology frontier, it comes up with their own opportunity and challenges. So while we are at India Space Congress, we thought that it would be good to bring the India perspective in this conversation. So taking the India perspective, I would like to ask Shashank that what unique opportunities do you see India have in this emerging domain?
Well, when people talk about orbital infrastructure, space computing, and India, so it's cliche, but India has been marked as a country that provides low-cost technology. But I would say if we were to press on that point, then I think we are missing the larger picture. India stands at a point where it can go beyond the low-cost infrastructure required for space computing and orbital infrastructure. See, we have already proved, we as in the country has already proved that we are capable of doing low-cost launches. Then we have various companies who are undertaking indigenous manufacturing. Then there are companies like Skyserve who have already accomplished edge computing. Then there's Take Me to Space, who's almost demonstrated orbital data centers. Then there are companies who are undertaking or planning to undertake debris removal. So you see, India has got the capability to provide complete full stack space architecture. And this is what is important. We as a country can go out there and provide a full solution. That solution has been validated in the Indian market. So India stands at a point where, we are not just another country who's trying to do orbital infrastructure and onboard computing, but we could be one of the nations who are sort of governing the entire process for the world.
Very, very interesting, Shashank. I'm sure that we have policymakers in the room and they're hearing you. And I think you are absolutely right that we need to see position ourselves not only as a cost-efficient country in terms of launches, but we also have to see that if we can aspire for bigger dreams and can actually shoot for that, right? So, and we do have the capability, as you correctly said. And so, Antonio, actually, that gives me a very nice segue for you to come and give us perspective. See, you have been in India, so you understand the strength that there is in India, and you also have an international perspective. So, from that perspective, why do you think so? Things like the AI manpower or AI literacy that we have in India, or obviously cost efficiency isn't there, or the software engineering excellence that is there in India. Do you see there is some advantage that is there for India to take lead in this sector?
If I say no to that question, that would mean I shouldn't have been invited to the panel. Of course, there is humongous opportunities for India, specifically because edge computing, orbital AI, and orbital data centers is not just a single project. It's not a single thing. It's a whole infrastructure. As mentioned, there's a technological aspect of it. There is the economic aspect of it. It is a platform very similar to what SpaceX did with the launch services. It wasn't just making better rockets. It was making a whole rocket economy using rockets as a whole platform. Like the rockets didn't become a good, it was a service. And orbital data centers is, again, a platform center. It doesn't, even if the technology is there, if you can solve all the radiation problem, vibration problem, the communication problem, etc., if the market isn't there, if the economics don't work out, it can't happen. How SpaceX solved it was that they were lucky. It was really good to be in the United States at that point of time where you could manufacture rockets. You had a bunch of engineers coming out of NASA and a lot of technology transfer also coming from NASA into SpaceX, and really a lot of funding coming from NASA as well. SpaceX wasn't really that unique in its constituency, but it actually was very unique in the timing and the environment that it was in. And also that is what I'm seeing for platforms similar to orbital data centers in India. India is now becoming a sovereign country with humongous inherent domestic capabilities. It can now do everything from launch to ground stations to everything in between, both upstream and downstream, which gives it a lot of flexibility and dynamics in actually experimenting with new platforms. So again, SpaceX was able to succeed in launch services because it had a huge domestic market first. It could then mature the technologies and then take it to the international market. And I think that's what's possible for India in orbital data centers. You have so many amazing engineers, because orbital data centers, you need to, as Sharat mentioned, you need to reinvent the whole thing. The chips may stay the same, but the algorithm needs to be latency allowed. It needs to be corruption allowed. But even if you just place a lot of GPUs up there, if the connectivity is with Earth as well as the inter-satellite link doesn't work, the orbital data center also doesn't have any problem, doesn't have any economic efficiencies. You have so many engineers, so many programmers who can solve it, who has matured out of the many call centers and data centers in India that you can take those expertise out of. Israel is also kind of, from an outsider perspective, is also going through a new kind of generational shift. You're seeing all these mature Indian engineers now graduating out of Israel and now providing consultancy or advisory positions to so many startups. And the Indian government, the Department of Space, has also kind of pushed in this Indian space sector to become more privatized. You're seeing an explosion of startups within space, and with federal funding as well as state funding from Gujarat, Karnataka, Tamil Nadu, also investing its own funding and attracting a lot of more startups. So from what I see as an outside perspective, India is really preparing itself for a big transformation into doing something new. It doesn't mean that orbital data center is that thing, but anything that is similar to infrastructure building, such as orbital data centers, India is now very well primed to actually take on such transformations. And that's why I think that if you're looking at orbital data centers, if any country can do it, right now US is kind of now maxed out, it's very saturated in terms of VCs and investments. I mean, SpaceX going public has still freed up some cash funding, but if you're still looking at a very sovereign-driven project, and for that, I do think India is more prepared than any other country right now.
Thank you for that perspective, Antonio. And I echo the same insight that I think we have all the right ingredients. We need to just be unafraid and try to cook it, you know. So and also very recently, I think there has been from our government officials also and from our ministers, I think the perspective that is coming out that in this whole AI stack, definitely India has a lot of playground in the application layer, and to run applications we will need really good data centers. So maybe some of the applications will drive the need for having these data centers. That is also another perspective which I think might be useful to think about. Coming back to Sharat, so what should India prioritize over say next 5 to 10 years, both from a technical and from a policy making perspective, to have a good position in this space?
I think it goes without saying that we need a lot more launches. I will not mince my words when I say that, because there's a lot of us engineers out there trying to build a lot of these space systems, and with the current launch cadence, we will not be able to gain the insights required to actually build a world-class product that can go beyond our borders and serve customers across the globe. we need a lot more launches. That is number one, period. From a policy perspective, like I was saying, adoption of these sandbox systems is something that is key. Apart from that, I mean, I think we'll have to wait for our white paper to come out for the next 2 days. But yeah, that's all I have to say.
Sure. No, we will definitely wait for that, and I'm sure there will be, and for everybody, I think that there should be some very interesting data there which we can look at. Now that we have talked about orbital data centers for a while, let's shift our gaze to edge AI, right? So, Shashank, I know you are very interested in that, but we'll start with Sharat this time. So Sharat, we know about edge AI on Earth, right? We have our Meta sunglasses, we have our fancy wearables, so and also in many industry applications as well. We are seeing edge AI being almost ubiquitous these days. But what does it mean to have being edge AI in space? If you can throw some light on that.
Um, uh, there's like multiple use cases to edge AI and how it is even perceived. I think there's different perceptions of it. I'll give you my take on it, which is for satellites. If you see the traditional way of working with a satellite is very ground based. It's all about you having absolute control over the satellite through your ground station, and then you sending it a command to do a particular task, and it happening very deterministically on the satellite. That's why if you see, typically if there's any issues with any satellites, it takes 2 to 3 months for the ground station teams to actually go back, talk to the engineering teams, figure out what went wrong and correct it the right way. It takes its own sweet time. That is a traditional approach. Now, a lot of today's systems, we are, again, with the advent of machine learning and whatever neural networks and AI that has come in, a lot of predictive maintenance, a lot of sensor fusion issues, a lot of things can potentially be diagnosed before they happen, given there is enough data provided to these models on both satellites itself. So from a bus maintenance, from a bus operations point of view, I think there's a great opportunity for edge AI to play a role. For example, I can take our own example where we're building star trackers with AI embedded in them, with edge AI. Now, I'm not saying we are doing away with the numerical methods or with the deterministic methods of a star tracker, but there are use cases that we see where our models could help, make the lost in space solution time faster, or know when certain issues or certain defects might be occurring. So think of it this way: edge AI sort of started, I think, in the industry from predictive maintenance, and then it went up the value chain. It sort of is starting there in satellites, is how I see it. That's my 2 cents on edge AI.
Okay. No, fair, because yes, you are absolutely right. So AGI applications, we see a lot of them in condition-based predictive maintenance, CVPM kind of use cases. Obviously, there are also other use cases in on Earth where we are seeing the application of AGI. But I just want to understand from an application perspective, Antonio, what AI workloads or what AI applications are most suited for orbital edge AI. So if you can name a few where applications or AI workloads are most suited for orbital edge AI.
And for audience who's maybe not too familiar with Edge AI, we are talking about taking AI and making decisions in orbit, in the spacecrafts themselves. And this is, again, very useful. The first line of application is, again, for Earth observation. When you have tons of data coming in from all different sectors, that is just not just like RGB, but hyperspectral camera, SAR sensors coming in, then you want to make decisions that are unique. You want to take information and intelligence out of these assets, then you want to be able to minimize the amount of time that it takes for decisions to happen, as well as the amount of the data that it takes for these decisions to happen. That is where we have Edge AI coming in to actually solve these problems, at least to a certain degree in space. So again, we do know that a lot of these decisions will have to be pulled. The great thing as well as the limitation of edge AI is that you need to do things in a limited constraint of time, in a limited amount of bandwidth and data and hardware you have available in the spacecraft. So we're not trying to say that edge AI can solve everything, but there are certain portions of the problem in the data decision-making chain that can be expedited by having that operations be conducted on board satellites. So Earth observation imagery analysis works because it solves, there is a very finite problem, which is you need to sort through a lot of terabytes of data, and then you need to actually figure out what data is useful to you, and we have so much models on this. And it solves the data problem because you already have data with algorithms to make it useful. The other side is actually autonomous operations. So autonomous operations is when you want to operate any kind of space. This can be rovers on the lunar surface, but majorly it goes into constellation management. As Sharat mentioned, a lot of times we're doing predictive maintenance or predictive modeling of these satellite constellations to make sure some maneuvers can be done, like spacing between satellites are done, or even like which satellites actually connect to a ground station to downlink data versus uplink data, etc. But with more and more satellites going up, both your own assets versus adversary assets or other third-party assets that you need to kind of communicate forward, you can't actually take decision-based criteria. You're now looking at the stochastic model of, hey, what are the percentages of us having usable data from this particular asset, using this particular ground station to downlink that data, versus having it communicate to another satellite, pass the data over there, and then downlinking it. So that kind of stochastic model is what we're looking forward to. So again, one is just utilizing data itself as the service, as the data layer. The second is autonomous operations, and like how do we then use edge AI capability to maximize the assets that we already have in orbit as compared to all the other assets that we also need to maneuver around.
Thank you, Anthony. You want to add something to that? So I have a question, and probably you can add in the same line. That I think one of the advantages that people talk about edge AI in orbit is that it can lead to a massive data reduction. But I would like you to quantify that a little bit. That what kind of an estimate, if you can give us a realistic estimate of what kind of data reduction we are looking at if we use edge AI for some of these AI applications that Antonio talked about. And since you are working in that space, so you can get as detailed as you want.
So I'll reserve this question for some time later, and I'll just follow on what Antonio brought out. And I'll try to give you a military perspective here. So for military decision makers and the top leadership, the information or the intelligence, as we like to call it, is important if it comes prior to the event or in fastest, shortest possible time. Now, delays can be really detrimental. So conventionally, the processes that are followed is, a satellite takes an imagery, it goes to a ground station, it goes to the user. From the user, it finally lands up to the decision maker. The timeline can be anywhere between 24 to 72 hours. And this is the best possible timelines I'm giving you. What Edge AI enables you is it reduces this timeline to action. With Edge AI, you can have insights delivered to you in about, say, 30 minutes. If you get the insights in 30 minutes, you can take an action in next 2 hours. So your 24 to 72 hours is reduced to 2.5 hours. So this is what Edge AI can do for you. The idea is, to make the decision better and faster. So this is what Edge AI can enable at least for the defense and the military. Now, coming to your question, how much data is actually compression is possible? So largely this depends a lot on the mission. Practically, if I were to put some numbers onto it, data compression can be anywhere up to 90%. On certain specific missions, say for example, in the case of maritime domain awareness, where we are trying to detect a vessel or a dark ship, the compressions can be somewhere about 98 to 99% as well. Because users in this particular case is very focused on, certain events, threats or alerts or something of that kind. So data compression to that capacity is possible. But just giving a little more perspective and a little more depth here, focusing only on data compression is, missing the larger goal. The goal is not to compress the data, reduce the bandwidth or the cost. the goal is to optimize and maximize the value of the data that is being transmitted. So the real challenge is not compressing the data. The real challenge is enabling that AI does not miss out any relevant information from that data.
Absolutely, absolutely. And I think you brought the latency point that you brought in, that we can actually optimize the latency in this process. I think that's a key insight. Yes, of course, data compression can lead to cost optimization as well, but latency specifically for time critical missions, this one minute or 1 hour can be of a huge value, right? And yes, the value of the information is something that we definitely also need to look at. Specifically when we are doing it on the edge, on the satellite itself. So if we can get as valuable information on the edge, on the satellite, and the device itself, as we can do on the Earth, taking a longer time, nothing like it, right? So, absolutely. So I think that sort of brings. We can conclude with this kind of our discussion here. I think we sort of traveled from orbital data centers to AGI to India's position on that, and I want to thank all my co-panelists for their insightful remarks. With that, I would like to open the forum for some few audience questions, since we have some time in hand. So please go ahead.
Hi. So my question is to Sharat. Actually, there are a couple of questions. The first one being, there is an approach which StarCloud has adopted, which is with a handful of engineers, they want to put compute in space and they are following that. While on the other hand, SpaceX has done it in the past and are trying to remodel it for the AI satellite. I also noted you briefly quoted that a lot of subsystems need to be done in-house to be able to bring in the technomics. Why? That's the question. And the second question, right now, what percentage of the EO satellite or the space application satellites is compatible with ISL links to be able to compute it in space and be able to derive insights? So these are the questions.
Great questions. So, firstly, why should subsystems be made in-house is your question, right? See, it's not, a lot of people think it's from a cost perspective. Cost is a very small lever here. Yes, for sure, cost, because if you go out there and try to buy a satellite or buy satellite systems, you will soon realize that most of it is imported. Especially, I'm giving an Indian context, number one. A lot of the critical stuff, let's say your ADCS systems, are all imported, and the sort of price tag on these things is not something that will justify a constellation cost. For a satellite or two, or let's say 5 satellites, it works out. The moment you start thinking constellation size, the unit economics do not work out. Given, I'm always comparing, so the way we do the maths is, we sell satellite time. And what we compare it with is AWS and Azure and GCP, Google Cloud Services. It's around some $0.02 a minute or at that price point, right? We start at $2 a minute of satellite time, because at the moment it's only Earth observation data for GIS industry. It is very important. That's the reason why we say asynchronous compute workloads are what are going up there, and not real-time compute applications immediately. It will come, but that cost about that $2 for a user, right? Sitting at a terminal, sitting on the laptop, it does not matter where the data center is. It's satellite, underwater. They care about that dollar per minute. As long as that cost, if you need to hit that cost, two things need to happen. Your own satellite cost needs to be as low as possible in the constellation. Number two, launch cost. As a satellite company, you do not have control over it, but launch cost is trending down again, thanks to whoever is in the industry. Now, what was your second question again?
What percentage of satellite is able to communicate through ISL links?
Right. So at the moment, see, ISL, it's very minuscule today. That's the reason if you see even we are, like we say we want to do data centers in space, but we are putting 9 meter per pixel imagers in our first 5 satellites. Purely for this reason, because there's not enough satellites out there equipped with RFISLs also to even give us data, right? And again, the whole ITU is its own process. So, again, Skyserve, a bunch of companies are helping solve this for the satellites which are going up from now. And that is significant too. It's not that it is a tiny amount, and what is already up there is, you know, what happens if we don't compute for satellites up there already. There's enough satellites going up with ISLs, with new age ISLs, which will be able to talk to this. The entire hypothesis breaks down if, like Anthony said, if there's no OISLs, this doesn't work. You really need to be able to compute data from other satellites in this network. Even though in the first 5 satellites we are putting imagers, 9 meter per pixel to begin with, then 1.5 meter per pixel, but after those, we do not want to be putting any imagers because there's enough Earth observation companies out there and we want to compute for them.
Got it. Thank you.
Thank you. Thank you for the question. We have one more.
I'm Manik. I'm from Telesat. We are a satellite operator, GEO, LEO, and we do space relay services for NASA and Planet as well. So we can talk. Question is, maybe this is for Sharat or for anyone. Putting the Earth observation AI capabilities aside, because that is already happening with NVIDIA and Planet have already launched that. But what is the next orbital rack or data center concept that you think will actually productized get launched, and by when would that use case be? Is it sovereign compute or sovereign storage? Because we see a lot of use cases for that. But what is that use case, and when do you think an actual product would get launched?
Yeah, I'll go first. Number one, I don't think it's done and dusted with Planet because they've just started. And again, see, access to this technology in space, or access at what cost and at what ease of access, and the user experience of accessing this and using it, I think is very, very important. Sure, Planet has existed for a long time, right? Great company, but the sort of pricing you have per square kilometer of imagery, I mean, Anthony would know. Yeah, a student in a college needs access to an imager plus AI in orbit. So I don't think the Earth observation industry is solved yet. I think that is the first thing that will get solved. But apart from that, you touched upon a very interesting piece, which is storage. Sovereign storage is the next big thing. Given the sensitivity of data centers, especially with the war that has recently happened that we've seen, data centers are these nerve centers where you want backups, it's like they're critical targets in any wartime situation. So we are seeing a lot of interest for storage and space solutions. But again, that opens a can of worms itself with radiation, with your redundant storage. But again, it's not like, satellites can't be bombed or they can't be approached, rendezvous proximity operations. Every country is trying to do RPO missions now, right? So, but there is a certain sense of security that it gives and a certain sort of distributed storage, again, so to say, because on ground, if you were to do it, again, the same problem with data centers, the time that it takes to build out systems like that. And a lot of people, again, I'll digress a little here, if you allow me, when they think of a data center, they only think server racks. No one has gone into a data center building and gone to the ground floors or the floors underneath that, where you will find the power equipment, where the dual substation power lines come in, and that power has to be conditioned and 100% uptime with backups running, and the cooling for it. It's not as trivial. So you can't just put up as many storage data centers on ground to solve this issue. So storage is something that will definitely get solved next. Some SAR, I think, is another, again, in the Earth observation domain, SAR generates humongous amounts of data. I think there's a lot to exploit in SAR as well.
Anthony, if you want to just add on to that.
Yes, so I'm really glad that you raised the question because this goes beyond the technology, like where is the market, where is the actual, who's gonna buy this? And the answer is really simple. If you ever go to any of the more defense-oriented conferences, like if you go to DevStat or if you go to Space Symposium, defense sector is literally the next big market. Like of course, if orbital data centers do become mature in about 10 years time, then you will see several applications for it. But the immediate application that almost any company should go for any high technology is national security and defense, because it does represent a humongous market. I mean, a humongous customer in itself with a very specific need with a problem that has to be solved. And like the reason that you see multiple PNT constellations coming up is that every country wants their own sovereign capabilities. The great thing about orbital data centers and edge AI computing is that you can do a lot of things secretly, without being traced, without being understood what these assets are doing. Only you know it. You have your own encryption, you can command these things, you can collect information at a certain wavelength to a very particular target. When I don't have as long a career as a lieutenant commander, but I also had a few years in the military where a lot of our intelligence gathering in G2 shops and then operationalizing in G3 and G5 shops literally relied on utilizing assets to the maximum capacity, and edge AI allows you to do it, and better yet, secretly, without understanding, without having that bottleneck of ground stations. Like if for civil side, ground station, that's just an economic bottleneck. For the military, being able to use less ground stations and being able to work with so much constraint in the amount of time you get, that is a strategic shift into winning. So orbital AI, what we will see is that these assets will store data, as Ashar mentioned, will store data sovereignly, and they will utilize their own algorithm to particularly find certain assets that you don't even want other companies to know, but they do want them to develop the algorithm to detect certain movements of certain assets, and then predict, like if one satellite detects something going on, then it will immediately tell the other satellites to start positioning their higher caliber sensors at particular wavelength to actually look at that data. So this multi-constellation, multi-orbit operation is where defense is spending a lot of money in, and that is exactly the gap that orbital data centers will be able to solve.
Both Sharat and Antonio has brought out very relevant points. I'll just add one single line there. Both the points are valid. We just have to ensure that there is a large-scale adoption to it.
Hope you guys got a lot of insights and a lot of interesting points to think over after this session. I just want to thank all my co-panelists. It's been an honor and privilege to host you guys, and I have learned so much. So thank you. I think one thing for sure, what I can understand, that I do not know whether this is going to be the next hyperscale platform, the space is orbital data centers, but definitely the computing does not need to stay confined within our dear Earth. It is now probably we are at that stage where it can move beyond Earth and can explore space. So thank you, and please give a very, very big round of applause to all my co-panelists. Thank you.
A very heartfelt thank you to our distinguished chair and esteemed panelists for an engaging future-focused discussion. Now may I please request all the panelists and the chair to kindly move forward for a group photograph. Please put a huge round of applause, ladies and gentlemen, for our esteemed panelists and our esteemed chair. Ladies and gentlemen, this brings us to the conclusion of Day 1 of the India Space Congress 2026. Today's discussions have highlighted the extraordinary pace of innovation across launch systems, orbital logistics, space policy, sovereign capabilities, and next-generation space infrastructure. On behalf of SIA-INDIA, I extend our sincere gratitude to all the speakers, moderators, chairs, delegates, partners, exhibitors, and participants for making today's discussion meaningful and impactful. Kindly join us for the closing and awards ceremony in the same hall after some time. Thank you and enjoy your day.